Welcome to Lesson 7.9, 10, 11, 12, and 13. Today we're going to talk about the periodic table. So we're going to start basically a little bit of history of the periodic table, how it's organized. We're going to move to electron configurations, and then we're going to look at periodic trends. So first, a little bit of background on the periodic table. The periodic table, there's a couple of names listed here at the beginning. Johann Deberiner and John Newlands. They did some initial research into the periodic table and thought that it should be, or at least be organized. One chose triads, another chose octaves. The modern periodic table is actually given the credit for the modern periodic table is given to Mendeleev, but Meyer was the one who suggested, Meyer and actually Moseley suggested that it be ordered in the way it is ordered now. But what Mendeleev did, and he is the biggest contributor, is he put it in order of atomic masses, and what he did is he just looked at different elements and realized that they behaved very similarly, and so he wanted to organize that. Moseley actually put them in order of atomic number, not atomic masses. So there are a couple places on the periodic table where they would be inverted had Mendeleev's plan stuck, because there are a couple places where the masses would have put the elements in a different order. So before we talk about electron configurations, let's talk about the off-bow principle. The off-bow principle basically says that as protons are added one by one to the nucleus to build up elements, electrons are similarly added to hydrogen-like orbitals. And then Hund's rule says that you have to have unpaired electrons before you have paired electrons. So if you'll look at the electron configuration of beryllium, it fills what we call the 1s orbital and then the 2s orbital, because beryllium is element number 4, has atomic number 4, and so therefore it will have 4 electrons in its atomic structure. The next one we look at when we look at Hund's rule is carbon, and so carbon has the 1s full, the 2s full, and then if you look over to the 2p boxes, notice that there are only that the final 6 electrons, electron 5, electron 6, are filling the 2p orbitals, but they're not in the same box. And so that's Hund's rule because that's the lowest energy. The valence electrons are the electrons in the outer energy level. So in this particular example, so let's look at carbon again. Carbon has 4 valence electrons because what you're looking for is the large number, and in that case the large number is 2. There's a 2s and a 2p. How many total electrons are in that outer energy level or energy level 2? There are 4 valence electrons. Those are your bonding electrons. You also have core electrons. So in both of these instances, the core electrons would be in the 1s orbitals. Elements in the same group have the same valence electron configuration. So for example, if we slip down here and we look at what's under carbon in this periodic table, so carbon is element number 6. And it's found right there. If you look under that, we have silicon. Silicon has the same outer shell electron configuration. So if I go back up to here, then silicon will be the same there, except instead of a 2, that would be a 3 in each instance. Okay. All right, let's go down here. You should have on your notes a blank periodic table. What I did here is I colored in the blocks. So if it's in the S block, the yellow represents the S block, and notice that helium over here is part of that S block. That means the valence electrons, if your element is located there, your valence electrons will be found in those blocks. So for example, the last electrons added to carbon, which was up here, would be in the p block, and that's what we saw on that orbital box diagram. Elements down here, they would be in the d block, and then here would be the f block. Electron configurations. So before we start those, some essential points. Labels for groups 1A, 2A, and so on indicate the total number of valence electrons for the atoms in this group. So a lot of periodic tables will have at the top of the groups like 1A, 2A, and then you go over here 3A and so on up to AA. And then here, these are your B groups. Those numbers in front of the A will indicate the number of valence electrons. The modern periodic table has 1, 2, and then it goes 3 through 12 here, and then it has 13, and then it goes to 18. So it goes across to 18. That is also useful for telling valence electrons. So this group has 1, this group has 2, and then just use the second part of this number, so 13 on up to 18. So the new group naming system is also works out well for that. Main group elements are those in the A's. And then your B groups are a little bit different, and we'll look at those. All right, so let's go up here. I wanted to, let's see. Okay, anyway, let's go down here and look at the practice. So your periodic table, or sorry, your notes does not have this periodic table because I wanted to put it in here so we could do these electron configurations. Okay, so let's do sulfur first. Sulfur is right here on the periodic table. Sulfur has 16 electrons that we need to account for. So when you do an electron configuration, you fill the lowest first. So basically you go from 1 up to 7. So that's the, boy, this pen is not writing very well. So that's the group numbers as you go down. And I think I skipped one because I wrote my numbers too big. And then you fill as you go along. So if you remember from the color and encoding, these are S's. And so we need to fill 16 electrons. So we're going to fill the 1s first. So we're going to put 2 electrons there. We're going to move down to the next row. Okay, so it's row 2. What block is first? The S block. And we're going to go ahead and put 2 electrons in there because there's 2 boxes across the S block. We move over here. We're still in the second row. We're in the P block, and we're going to count across. We can put 6 electrons in that P block. Move down a row, and we put 2 electrons in the S. Still, we're going to move over here, and we're going to put only 4 electrons in the P because to get to sulfur, we only have to go over 4 boxes. So it's about filling and knowing which block you're in. So if you have a periodic table, you just do it that way. So if you look down here, that's the electron configuration for sulfur. The second one is the noble gas notation. So if you want to do noble gas notation, that just means you find the noble gas prior to. So since this is element number 16, the noble gas prior is element 10 or neon. So you put neon in square brackets, and then you do as we did already. What do you do after neon? You go down to row 3, fill the S block, and so on. Okay, so there's a couple more examples there. The next one, the cadmium is found right here. So in cadmium, we have to account for 48 electrons. So the added rule to that one, you'll notice you go along just fine till you get to the 4s. We've been, follow the same rules. And then the D block is 1 less than the S block. So when you get to the D's, it's going to be N minus 1. So it's going to be whatever the row number is minus 1. So this will be the 3D. This is going to be the 4D, 5D, and 6D. And I didn't get these row numbers put in there very well, but that's what those would be. Okay. So And then on the F's are going to be the row number minus 2. So this one actually fits with row number 6, and this one with row number 7. So this is going to be the 4F, and this is going to be the 5F. Okay, so go ahead and practice with those. If you have questions, look back at the answers and try to figure out how you got that. Practice problem number 2 says how many of the following electron configurations are in their for the species in their ground state are correct. Ground state electron configurations are what we were just doing. That just means the electrons are going to be where you expect them to be based on following the periodic table and putting them in. You'll notice on this one, let's see, 1s2, 2s2, 2p6, 3s1. Well, that looks like it fits, except magnesium is right here, so you should go over 2 on the S's. So look through those and try to figure out what's wrong with those. The red ones are the ones that are correct. In which of the following groups do all the elements have the same number of valence electrons? So you're just kind of looking at each group here. And what you're going to look at, you're going to try to see if they're in the same vertical column on the periodic table. And obviously there's none of these that's highlighted, so go through and look at those and make sure you understand why none of those are. Of the following elements, which has occupied d orbitals in a ground state neutral atom? When you look at those, you're going to find that in order to have any d electrons, you have to get to element number 21. And the only one of those that has an atomic number greater than 21 is going to be barium. All right, so just some trends with the periodic table. One trend is ionization energy. Ionization energy is the energy required to remove an electron from a gaseous atom or ion. Excuse me. There are some elements that would like to lose electrons and some that want to kind of hold on to their electrons. So you'll notice, let's look across row 2 here. Lithium has a very low ionization energy. Neon has a very high ionization energy. Because lithium has one valence electron. If it loses an electron, it becomes very stable because it won't have a full outer shell. So it would love to lose that electron, so it doesn't take very much energy to pull that off. Neon, on the other hand, already has a full outer shell. It's not going to want to lose that electron because if it loses that electron, then it no longer has a full outer shell. Okay. So let's look at concept check 1. Look at the values of the first ionization energies in the table below. Explain why the numbers would increase or decrease like they do. Okay, so they're going to increase as you move across the row because they don't want to lose electrons, but they're going to decrease as you move down a row because if you think about what's happening as you move down a row, here's the nucleus, and then I add layers of electrons. Well, the farther those electrons get from that positive nucleus, then the easier they are to pull off. Okay? So ionization energies increase it up and then across. So the biggest ones are going to be found at the top, and the smaller ones are going to be found at the bottom. First ionization energy for phosphorus is 1060. Sulfur is 1005. Why? Okay, so if you look at about what's happening right here, phosphorus in its p orbitals, so there's your electron box diagram. Phosphorus looks like that. Sulfur looks like that. Atoms are stable when they have half full shells, and so it's going to be easier to pull this electron off of sulfur than it is to pull one of those electrons off phosphorus. So most stable state is full shells. The next most stable state is half full shells. Electron affinity is the energy change associated with the addition of electron to a gaseous atom Fluorine is the element with the highest electron affinity. That means it's going to have the greatest change in energy if I add an electron. And that's because fluorine wants an electron to reach a full outer shell, and it's close to the nucleus, and so that electron is going to have a lot of pull. If I can add it, the nucleus is going to have a lot of pull because it's basically very close to the nucleus. Francium does not want an electron, so putting an electron in it is not going to change its energy very much, um, and it's very far away from the nucleus, that electron that you add. Atomic radii decreases as you move across the period, increases as you move down a group. So atomic radii makes sense on the moving down a group, because as you move down a group, that means you're just adding layers, and so it makes sense that it gets bigger. It decreases as you move across, because every time when you're moving across the periodic table, you're adding protons. And what you're doing, so every time you're adding a proton as you move across the period, then it pulls the electrons in tighter, because you're at the same distance from the nucleus, but you keep adding more positive charge, and that pulls them in tighter. So that's why you get smaller as you move across the periodic table. In terms of ions, the same kind of thing. You're talking about how far away the electrons are from the nucleus and how much it pulls it in. So strontium, because it has the most protons, is actually, all of these are in the same column. So beryllium, because it has the least number of protons, is going to be um, the smallest, because you're talking about layers here. Okay. Um, and then some other trend sizes. So just kind of look at these and figure out what you think, and based on trend sizes and ions and things like that. Please look in your book. There are lots of diagrams that show the atomic radii, and pictorially kind of comparison makes it look kind of like little marbles. All right, let's finish up with some other information on the periodic table. There's the group names. Group 1 are your alkali metals, 2 alkaline earth metals. Move over to the right side of the periodic table. 7A are your halogens, 8A your noble gases. Your B groups are your transition metals, your bottom 2 rows, the top rows, your lanthanides, the bottom rows, your actinides. Another thing about the periodic table, there's a, a stair-step line over here that separates metals from nonmetals. So on this particular one, the blue elements represent your metalloids, so they have properties of both metals and nonmetals. Your metals are on the upper right of the periodic table, with the exception of hydrogen. Hydrogen is also a nonmetal, but it hangs out in the alkali group. And then there are a lot of metals on the periodic table, um, including your lanthanides and actinides. All right, I know that was a long lesson with a lot of information, so please refer to any outside resources like your textbook, and to clarify anything that you need clarified. All right, I will see you next time.